Our 30 minutes. The first speaker is James Hughes, who is a KG student in computer science here, working in Mark Daly's lab, who gave the introductory note to that conference. So, James.
Thank you. So, as the chair just said, I am in computer science, and I'm actually also affiliated with the Brain and Mind Institute here. There's a neuroscientist. But I have a very unusual problem. Despite the fact that I'm in computer scientists love to tell me that my work isn't computer science. And the neuroscientists like to tell me that my work isn't neuroscience and it's useless. So I have to admit I'm really excited to have the opportunity to finally speak to mathematicians, as I'm hoping you'll be able to tell me that my work has nothing to do with mathematics. So we'll find out in a few minutes. So another heads up too, this is a very, very applied form of computer science. So it's very applied stuff, so bear with me for a little bit. So I like to fiddle around with numbers a lot. I like to model things. I like to hack away at the numbers, screw around with them, and maybe get a little better. Try things, did it work, did it not work, try it again. I'm assuming a lot of people in this room kind of have the same approach to a lot of the work they do. They just like fiddling with things. But I'm a computer scientist, and I'm exceptionally lazy. Computer scientists, that's why they do what they do, right? Get the computer to do all the work for you. I always think, wouldn't it be great if I can get the computer to basically do all my work for me? Well, hang in there for a second. So, now some of you might be aware of this thing. Now this isn't my video, but I'm going to have it play. Well, I explain a little bit about evolutionary algorithms. Anyone here heard of these things before? A couple people. Yeah, okay, good. So basically the idea is, it's a type of artificial intelligence, machine learning, where it's driven by, loosely based off of the theory of evolution. If you have two reasonably good solutions to a given problem, for example, cars driving on this two-dimensional road here, maybe if we take these two reasonably good solutions and we mix them together and pull them apart, maybe we'll get something better. Maybe we won't, I don't know, but maybe it'll get better. And at the very least, maybe if we take one that's pretty good but we change it a little bit, maybe it'll get better. Maybe. And actually, they tend to. As you can see, these cars, over time, are getting increasingly better at driving on this little road here. And it does usually take some time. Go to the next slide. Perfect. It does usually take some time. I'm going to skip ahead here. So here's another one where they're evolving little robots and virtual robots to walk. You can see that the generations, that's like iterations. Now these aren't my videos, I just stole them from somebody else. And you can see at first they suck, and they get a little bit better, but after a while they get pretty darn good. And I know, I love this. These evolutionary algorithms aren't just used to evolve little cars and little virtual robots. They're used for a whole bunch of things. You know what, I'll skip to my favorite part of this video. It's not necessarily relevant to what I'm going to be talking about, but it's worth showing. Where is it? So here's, you'll see in a moment, there's a robot evolved to walk on a slope with curves as 3-kilogram objects are being thrown at him. And he's pretty good. These computer scientists were clearly sadistic. I don't know. Anyways, this is the type of stuff I like to screw around with. Okay. So, anyways, these evolutionary algorithms actually have been applied to a lot of things. They've been applied for programming real robots. That's done a lot, actually. Designing buildings, art, music, stock market trading. What else do I have listed? Oh, and NASA actually designed some antennas on some satellites in space with evolutionary algorithms, because they were just much better at their job than any engineer had designed. And another really interesting application is circuit design. Evolutionary algorithms are really good at designing circuits, which actually brought up some interesting problems, because some of these circuits were patented. And I mean, based off of what it means to get a patent for something, I mean, these evolutionary algorithms have no domain knowledge. They're not electrical engineers, but they're able to design circuits way better than electrical engineers and recreate already patented things. So it kind of brings up interesting issues. But these things are pretty powerful. Now, I'm particularly interested with a very special kind of evolutionary algorithm called genetic programming. genetic programming, it's evolutionary algorithm, but the problem being solved is, well, how do I write a program to solve a problem? So it's an evolutionary algorithm that writes algorithms to solve problems. So the computer is writing computer programs. And these programs can be done for a whole bunch of things. I'm going to skip this because it's awfully distracting. It's fun to watch. But there's a very special kind of genetic programming. It's a relatively simple kind of genetic programming called symbolic regression. It's a type of regression analysis that searches for declarative mathematical expressions to find relationships in data. So here's like an example of symbolic regression. This one actually I don't think was done with an evolutionary algorithm. It was a different type of algorithm. But I think this is the absolute value function there, and it's fitting. It's basically like curve fitting. And because it's a relatively simple form of genetic programming, we can get a lot of enhancements out of it. We can hack away at it to speed things up, make it better. So if you wanted to do symbolic regression yourself, you can implement genetic programming, and it would probably do a pretty good job, but in order for it to be like really good and competitive, you gotta really hack away at the algorithm to make it just a little bit better. So it's just regression. I mean, we all know what linear regression is. We've got some data, right? And you want to fit, all right? So you got this. Do your old linear regression, you know, blah, 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 and you get this, you know. You get something equals some variable times a coefficient plus some variable times a coefficient plus some variable times a coefficient, so on and so on and so on. But all it can really do is just give you a multiplication of coefficients and some additions, right? But with symbolic regression, you can make your expressions look like basically anything you want. Here's just a quick, simple example. With symbolic regression, you're picking the operators, or functions, whatever, how they're used, you're picking the coefficients, you're picking the variables. You don't just pick the coefficients like linear regression is doing. You can make it look like anything you want. And you could have operators, whatever you want. If you wanted, you could make it do integration. Now, that would probably be really slow, but it probably could. You could, anything you want, really. So I went out and I wrote the code to do symbolic regression. And I ripped all my stuff off of a researcher who had Hod Lipson, who's currently at Columbia, but at the time he was at Cornell. So I ripped off all his work from when he was at Cornell. And I wrote the GP system, genetic programming system, to do symbolic regression. And I told my supervisor, it's done, I know it works. And he's like, okay, well, prove it. Because he hasn't really played around with the stuff, Mark. He knew about it, but he wanted to see how good is it. So he sent me data files that looked like this, basically. They weren't as big. It's just data. So he started off with simple things. I had to find the function. He gave me the data, and he said, well, what function gives you this data? And I think he started with just like x plus y, ran it, found it, no problem. Then he get a little more complicated, x plus y divided by z, no problem. A little more complicated, a little more complicated, a little more complicated, and every time found it easily. Easy, easy, easy. We were getting pretty excited, and then he thought, you know what? Because he knew, because when you write symbolic regression, when you write the code, you have to tell it what are the basis functions you want to allow. And he asked me, and I said, well, right now I only have it using, you know, the trig stuff. I've got e, log, and addition, subtraction, multiplication, division, you know, simple stuff. So he said, okay, I got him. He gives me this. He gives me the data for this. Gamma function, right? This is what it looks like. He didn't tell me he was giving me a gamma function. He just gave me a data file, CSV. And in fact, he gave me these data points. I think there's about 1,000 here. Okay, he gave me these data points. And I hit run. It took a little bit longer. But it found this. Can you see the red line? No, it's not perfect, right? It's did pretty good here, but it kind of crapped out over here. But I'll tell you why it crapped out. Because, I mean, there was only like a couple data points. Like, look at all the data points it hit. It looked like it misses like 1, 2, 3, 4, 5. Probably, if I got more to the left, might have done a better job. And it kind of didn't do too good of a job up here. It starts to spread away from what the real gamma function is. But then again, I've got no data points over there, so it couldn't fit to it. So I need to be very clear. I didn't find this. I didn't find it. In fact, here's the expression. That's what it looks like. It's ugly. But for whatever reason, this is a wonderful approximation of the gamma function between about 3 and -2.5. But I didn't find this. I didn't. The computer did. The computer came up with a hypothesis, it tested it, and made some changes accordingly. And did it over and over and over and over again, a lot of times. And it found something. So I didn't find it. The computer was the scientist. I didn't do this. I was just his secretary. I was telling him just do this for me, and then it did. So I didn't find it. The computer did, and that's fantastic. So let's take a step back and ask, well, okay, so are there any neuroscientists in this room right now?
You're safe.
I'm saying good, because I was just going to say no, I can make fun of them. I'm allowed to because I'm like a pseudo-neuroscientist right now. fMRI, functional magnetic resonance imaging, I put you in there and I can look at your brain. We zoom in on your brain and we can look at individual pixels, but of course the brain's three-dimensional, so really it's a voxel, a three-dimensional pixel. And I put you in the scanner and I have you do something. Maybe I tell you to move your hands around a little bit, squeeze them, do something. And I look at the voxels in your brain, and over time, as you're doing different things, the voxels, they change. The intensity of the signal we're recording inside of them change. They change. But of course, we're not looking at just one voxel, we're looking at tens of thousands of voxels over time. And we get data that looks like this. You know, it's just a whole bunch of data. It's time series. We got data points over time. So now a neuroscientist, they want to create a model for this. Like, well, how does this data interact with itself? Like, what's it look like? So they want to do linear regression, because that's what they always do. And now it depends on what you want to do. Maybe they'll do it with all voxels, but that takes ages. But they'll break it down into regions of interest, so they'll average it over, I've got 30 here. In fact, there's 30 columns. 30 regions of interest, the average voxel intensity in that region of interest for each time point. There's 284 time points, not all of them are shown. And this is for a very specific motor task I was looking at. So they got this data, but of course not all 30 regions of interest might be important for the linear regression, so they do some sort of thresholding. They do linear correlation, then maybe they do false discovery rate, Baum-Forney correction or something. And then they end up with, okay, these are the relevant regions of interest, and then they do linear regression. There's a problem with linear regression. So here's a picture I stole from Wikipedia. We see here on the second row, these are beautifully linearly correlated data. The top row we see as the data spreads out, they lose their correlation. In this bottom row, there's 0. So that means there's nothing interesting going on there, right? You look at that, it's boring, isn't it? Nothing fancy. Of course that's ridiculous. There's clearly something happening there. But if you use some linear tools, it would say, no, there's nothing. And you know what? Who here thinks the brain's a linear system? Nobody. That's ridiculous. Of course not. So the neuroscientists are using all of these linear tools to study a system we know isn't linear. Now, to be fair, I tease them a little bit, but to be fair, it's non-trivial to just find nonlinear relationships. You can't just find nonlinear relationships. Right? It's not easy to do. And I'm not saying that the work done to date is no good. Okay? There's a lot of fantastic neuroscience that's been done with the simple linear tools, which might concern you, as it does me a little bit, but clearly there's been great work done. So, not to make fun of them too much, just as a heads up. So our goal is we've got this symbolic regression system that can find nonlinear relationships. So why not have the computer, why not have this little scientist right here look for the models? And we want to find the relationships between regions of interest within the fMRI time series data. And we want to hopefully find these nice, accurate, succinct models that are going to be better than the linear ones at understanding the physiological connectivities in the brain. Because as a heads up, I don't know if you know this, but we really don't know much about the brain. I remember coming into the neuroscience thinking like, oh, this is going to be great. And then I started learning about it and I realized like, wait, we don't really know anything at all. Which is great because now there's a lot of opportunity to actually discover stuff. So let's see what happens. So I run my GP system on, I picked 100 subjects over 7 tasks. And I wanted to model it all. Originally I did a lot more on one task, but I broadened the search. And I ran it, and it finds them. It finds them easy, no problem. I let mine run for like I don't know, there was like 1 trillion iterations really that happened. And that took a couple hours, but that was overkill. It ran for orders of magnitude longer than it needed to, but you gotta remember, I'm looking for the best model possible, so I figured I'll let it run for a long time and let's see what happens. And here's an example of one. That's very nonlinear, isn't it? And I've got this graph shown right here. The R's are like the variables. And you'll see that the regions of interest, the red lines are strictly nonlinear. Blue, there's a little bit of both. And black are strictly linear relationships. And not many are strictly linear. So let's see how it compares. So here's some data of region of interest 21. This was the motor task. That's primary motor cortex. And this is the time series plotted. And as a heads up, the data is very noisy in the fMRI stuff. It's a big criticism of the field, so heads up. And here's my model, the nonlinear model. Fits pretty well, doesn't it? It's not perfect. And it has a mean absolute error of about 10.82. So how does it compare to a linear model? All right, the nonlinear model has to be better, right? It has to be. Oh, crap. It wasn't. That doesn't make any sense, does it? The nonlinear model is supposed to be better, isn't it? It actually can make the data better. Well, all right, let's take a step back and let's look at some. Here's an example of a nonlinear model. This is the one actually I just plotted, the red line. What do we got? Region of interest 12 equals all, or 21 equals all that. There's 6 regions of interest in there. Let's look at the linear model. Okay, there's 28 there. Well, it's because of the thresholding technique. When I did thresholding, because it's based off of correlation, Pearson product, just linear correlation, it still says everything is linearly related. And remember that the brain is one system, so it's not unusual that parts of the same system are maybe linearly related. So the thresholding techniques said that there's 28. So now I had 28 things to fit to the data. Now maybe all of these regions of interest really are that important. Maybe they are, I don't know. Symbolic regression didn't really like them. It didn't pick 28. It could have. It only picked 6 though, but this one, and it was better. So I don't know what's going on. There's 28. And in fact, if you look at all of the subjects over all the tasks, it depended on the task, but a lot of them had a lot of regions of interest that are related. So then I generated this plot. It's a bit to chew on, so hang in here with me for a second. Along the x, we've got task. Along over here, we've got numbers of regions of interest that were used to generate a linear model. So when it says 2, then I just fit it. Really, it was only 1 because left-hand side, right-hand side. I fit the one, the most linearly correlated region of interest I used to generate the linear model, and then I did the top, then like 3, 4, 5, 6, 7 to generate. And here is the p-value. Maybe you test to say, is there a real difference over the 102 subjects time series over all the tasks? So basically what you're seeing here is a transition from when the nonlinear models were better to when the linear models were definitely better for each task. And you'll see language. Ooh. And down here, false discovery rate, FDR, on average, for the emotion task over all subjects, it wanted 24.8 regions of interest in the model. 28, 27. Von Froning correction was a little more conservative. Still had like 21, 27, 25. So the linear models still wanted to fit so much. But the nonlinear models had only like 3.5, 4.3. And like, let's look at language here. The nonlinear models were better than the linear models up until, it was definitely better up until about 11 regions of interest. Then it started to get better around 14, 15, 16. So the linear model needed like 14, 15, 16 regions of interest. It had these degrees of freedom to fit the data. Then it could finally beat the nonlinear models. Now maybe I'm kind of cheating. I don't know. Maybe I'm kind of cheating. I don't know. But what I'm seeing is the nonlinear models are finding these relationships that do exist. These things are clearly nonlinearly related. And the models can fit the data more succinctly, better, kind of, maybe I'm cheating, I don't know. But symbolic regression is clearly a good choice. This computer is doing a pretty good job with the experimenting, figuring out what's going on, describing the data. And I've got a lot of directions to take this, because this is still very preliminary work. We need to look at what happens if we look at the brain with other modalities like EEG or MEG. Don't ask me to say what those stand for. It's like magna something complicated. And I wonder how the models can generalize across subjects. I want to incorporate other genetic programming enhancements to see if I can maybe make it a little better still. And the other one, I really want to look at the data. I want to look at the models, rip them open, and see what's going on. And in fact, just about Wednesday morning, I did that. And so, hang in here, because these aren't the best plots, because this is very last-minute stuff. At the top, we have region of interest. On the left there, we've got the task: emotion, gambling, language, motor, whatever. And here is a count. So over the 102 subjects, I did 102 for each task, same 102 for each of the different tasks. It was the number of times the region of interest was in a linear model when it had the same number of regions of interest that the nonlinear models found. Right? So an even number of regions of interest. And you'll see that 7, 2, and these ones, they all have 100 because they were forced to be in the expression. They were the left-hand side of the equation. And then we've got the same thing, but for the nonlinear models, just whatever symbolic regression found. And this plot here shows the difference. Very red ones, because this is linear minus nonlinear, very red ones show that the linear models had a lot of this region of interest, but the nonlinear models didn't really. And very dark blue are the opposite. The nonlinear models had them, but the linear models didn't really care. And I want to focus your attention to the language task here. Region of interest 27. The nonlinear models loved that one, but the linears didn't. And region of interest like 21, 22, the linear models loved these, but symbolic regression, the nonlinear ones didn't really care for these. That's interesting, isn't it? So, well, let's look at the Pearson correlation. So keep your eye on that really dark blue one. So it's right here. It was the 30th, it was the least linearly correlated region of interest. The least linearly correlated. But symbolic regression, despite it being not linearly correlated, because why would it have to be linearly correlated to be meaningful? The least linearly correlated region of interest, symbolic regression loved it. And the third and fifth, symbolic regression, despite being very linearly correlated, symbolic regression didn't care for it. Nonlinear models didn't really help. So that's interesting. Don't ask me about this though, because this is just from Wednesday. I haven't thought too much about it. So anyways, I'd like everybody to join me in thanking my computer for this fantastic, interesting stuff.